Okay, so we are just beginning Chapter 5 of Introduction to Statistical Learning. Okay. These are conceptual questions. We're on question 1. All right, so here's the question, but I'll give an explanation of the question here in a second, which will be required if you haven't read the chapter. So using basic statistical properties of variance, as well as single variable calculus, derive equation 5.6, and I've reproduced 5.6 right here. In other words, prove that alpha, that this expression right here, minimizes the variance of this expression. Okay, so really to make sense of all of this, we're going to need the context that the book gives where alpha is coming from and why we're minimizing this and that. So the idea that's presented in the book is that we're going to invest some proportion of our money, and we'll call that proportion alpha, into an investment that has an expected return of x. The rest of our money, 1 minus alpha, will go into investment with an expected return of y. So our expected return is given here. And we want to minimize the risk of our investment. In other words, we want to minimize the variance of our return. We want to minimize the variance of this expression right here. So that's what we're going to do. So first, we need to derive an expression for variance of this guy. Okay, and as we do that, we're going to use these 3 rules right here. So the first one is that the variance of x plus y is the variance of x plus the variance of y plus 2 times the covariance of x and y. Now note that the x's and the y's here just refer to generic variables. They don't necessarily refer to the x and y given on our problem. They certainly can, but it's a general statement. The next property that we'll use is given right here. So the variance of a constant times a variable is equal to the constant squared times the variance of the variable. Now again, alpha is not to be confused, or I'm sorry, a in the rule here is not to be confused with alpha, okay? It's just a generic constant. And indeed, alpha will be a constant. And so this rule applies to alpha, but it's a general rule. Okay, finally, the covariance of ax plus by equals ab times the covariance of xy, where a and b are constants, x and y's are variables. This is the rule. Okay. So what we want to do is, first, we want to find the variance of our expected return. So we want to find this right here, okay? And then we want to minimize it. So first thing we need to do is come up with an expression for this, okay? We can't really minimize this. We have to find an expression that we can work with. Okay. So the first thing I'm going to do is apply Rule 1, because what I have in what we're trying to look for here is the variance of one entity plus the variance of another. So I have the variance of ax, okay, plus the variance of 1 minus alpha y, plus 2 times the covariance of the 2 times the covariance of the 2 entities, okay? Just like we have up here. All right. Next, I am, for these 2 terms here, I notice that I have the variance of a constant, whether it's alpha or 1 minus alpha, and a variable, x and y. So I'm going to apply Rule 2. So I just take the constant out. I have alpha squared times the variance of x. So the variance of alpha x equals alpha squared times the variance of x. The variance of 1 minus alpha y is equal to 1 minus alpha squared times the variance of y. Okay. And then for the covariance term here, I'm going to apply Rule 3, right? And Rule 3 says that if I have the covariance of constants and variances, or I'm sorry, of constants and variables, then I take the constants out and multiply those by the covariance, okay? So I'm going to take the constant out. I'm going to take this constant out, 1 minus alpha, that goes there, times the covariance of x and y, and remember that there's a 2 here, and that 2 just hangs out there, all right? Okay, so now in step 3, I'm going to do 2 things. I'm going to just start to use symbols so that we match our formula up here, and I'm also going to expand some terms, all right? So here I have alpha squared times the variance of x, so that just becomes alpha squared times sigma squared x, right, where sigma squared x is the variance of x, okay? Similarly, the variance of y is sigma squared y, okay? And this term, 1 minus alpha squared, just expands to that. Okay. Now this expression here, I'm going to multiply the alpha through, so I have alpha minus alpha squared, and the 2 just stays there, and I'm turning the covariance of x and y into sigma sub xy. Okay. And now for my final step, I'm just going to multiply through anything that can be distributed. So these guys. Okay. So this term just drops down. 1 times the variance of y is the variance of y. Negative 2 alpha times the variance of y is negative 2 alpha variance of y. Alpha squared variance of y is alpha squared variance of y. Da, 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 da. Okay. And again, I'm just going to do something similar here where I'm multiplying 2 alpha through here and 2 negative alpha squared here. Okay. So this is our final expression for the variance of our expected return. All right. Now, so as to not lose sight of what we're doing, we want to minimize this expression here. All right. So to do that, we're going to take its first derivative and set it equal to 0, and then later we'll check to make sure that it's a minimum. Okay. So let's do that. So so I'm taking my derivative with respect to alpha, right? Because we want to find the alpha that minimizes the variance. Okay. So I take the derivative with respect to alpha of this expression, right? This expression right here. Okay. And when I do that, you can do it for you can demonstrate this to yourself, but I come out with this. Okay. And notice that everything is headed off by a 2 or a 4, so I'm just going to divide everything through by 2 just because it's easier. Okay. And then I'm going to set this value equal to 0, right? That's how we find a minimum or maximum. We find where the derivative of the expression is 0. Okay. So when I set it equal to 0, now I want to solve for alpha, so I'm going to put all of the terms with alpha on one side of that equation, right? So I have this, and this. Those all stay over here, and then the variance of y and this covariance of x and y are going to go to the other side. Okay, so I have all this. So now I have an alpha in these 3 terms here, so I can take it out, which is very nice because I want to ultimately just isolate alpha, and so I divide both sides through by the parenthetical term, and I come out with this, which is the expression that we were looking for up here. Okay, so that's good. But the final thing that we want to do is to make sure that when we found the derivative, when we found the alpha at which the derivative equaled 0, or how do I want to say that? When we found that, how do I want to say that? That we have correctly identified a minimum rather than a maximum, right? Because remember, when the derivative is 0, it can be either, and so we want to put it through the second derivative test, okay? So I'm just going to take the second derivative of my expression for variance, okay? Well, that's the same thing as taking the first derivative of the derivative of the variance, or of our expression, okay? So I'm just taking the derivative of what we've already found, okay? And when I with respect to alpha, and so when I do that, I get the variance of x. There's no alpha here, and so this term drops out. I get the variance of y. This term drops out because there's no alpha, and then 2 sigma xy, or 2 times the covariance of x and y. All right. Well, when I look at this, I immediately identify the fact that this is the variance of x and y. This is, by rule 1 up here, this is what variance of x and y is. Okay. And because variances are always, oops, I don't like that. Because the variances are, sorry about that. Because the variances are always greater than or equal to 0, the second derivative is positive. Okay, right? So the variance of x and y is the second derivative of our expression, and because it's positive, we know that we have found a minimum. Okay, so anyway, that is it for this one.